Hey guys, sorry, I had some technical difficulties, so the video sort of cut off in the middle of the problem, so I apologize for that. Let me pick up where I left off. Okay? So, let me get back to reasonable starting point. Okay. So in this one, we had just gotten to the point where we are going to try to figure out exactly how much of our sodium formate and our formic acid that we need to start off with. So let's just sort of revisit some parameters. All right. Our target pH is 4.0. One thing I don't know that I told you or not was the total target volume of solution that we're making. All right. So let's just make it simple. Let's say we're trying to make 1 liter of solution. All right. I also haven't told you the molarity, the concentration of the formic acid that we're starting off with. That's going to be important. So we're just going to assume that we're going to start off with a pretty concentrated solution. We're going to start off with a 10 molar solution of formic acid. All right, and then we're starting off with crystalline, solid sodium formate. All right. Okay, so remember the ratio that we want of the base form, which is the formate, versus the acid form, which is the formic acid. We want that to be a ratio of 1.78, right? Or 1.78 to 1. So the most direct way of doing that is just to simply try to target the inclusion of 1.78 moles of formate and 1 mole of formic acid. All right, so if you do it that way, let's start off with the formic acid. So, we can use the good old molarity formula. Molarity equals moles of solute per liters of solution, right? We're starting off with 10 molar formic acid. We're trying to get 1 mole of it, and we're looking for the volume. All right, so you would solve for L, and in that case, L is going to equal 1 divided by 10, which would be 0.1 liters, and that's equivalent to 100 milliliters. So that's half your problem right there. What you would do is you would measure out 100 milliliters of formic acid, put it into your container. And that would give you the 1 mole of formic acid that you need. Okay? All right, so then you would need to figure out how much sodium formate that you need. All right? So sodium formate, when it dissociates, it gives off sodium and the formate ion in the 1-to-1 ratio. So for every sodium formate that decomposes, or dissociates, you're going to form 1 mole of formate. All right? So if you can figure out how many grams of sodium formate it takes to give you 1.78 moles, then we can assume that would also have 1.78 moles of your formate ion. All right, so here's what we're going to do. We're going to look at the molecular weight of sodium formate because that's the unit that has both grams and moles in it. All right, so sodium formate has a molecular weight of 68.01 grams per mole. All right. We know that we want, hiccups. Erase this. All right. We know that we want 1.78 moles of sodium formate. We just don't know how many grams that's going to be. So solve for the number of grams. All right, so what you do is multiply 68.01 times 1.78. And that comes out to be about 121.1 grams of sodium formate. That is what gives you 1.878 moles of sodium formate. And since we know it dissociates in a 1-to-1 ratio, that also means it gives you 1.78 moles of formate ion. So that's the second half, right? You would take 100 mils of formic acid, add it to your container. You'd measure out 121.1 grams of sodium formate, add it to your container, and then just dilute the solution with water until you get 1 liter. And then boom, you have 1 liter of a formic acid buffer solution, pH of 4. Woohoo. All right. I do want to highlight one thing here. I'm going to keep the rest of this up and erase this part. This is just one way that you could do it. This is actually a pretty concentrated buffer solution because we have 100 mils of 10 molar formic acid. That's a lot. 121.1 grams of sodium formate. That's a lot. That is great if you want a really high buffering capacity. That would work fantastic. Now, if you didn't need that much, right, and you wanted to save on materials and supplies, you could scale this down as long as the ratios, good Lord, didn't mean to make it that fat. As long as the ratio is still 1.78 to 1, then you're good. So, we talked about using 1.78 moles of formate and 1 mole of formic acid. You can scale both of those back down by maybe like a factor of 10 or something. You could use instead 0.178 moles of formic acid, formate, and 0.1 mole of formic acid. Still in the same ratio, right? It just means that you wouldn't have to use quite as much of either one. So whichever one of these is fine. Either one of these produces a perfectly good buffer at 4. The more concentrated one forms, the more longer lasting as far as buffering capacity. All right. So that's one way that you can make buffers, is from starting with individual sources of the acid and the conjugate base. You can also do it by just starting off with completely with one of them, and then using something else to convert it into the other form. All right. So here I'm gonna just put this equilibrium up again, just so you can have it as reference. Let's say instead of having formic acid and sodium formate at the beginning, you just had sodium formate. You're going to be starting with crystalline sodium formate. And instead, it's really ugly. One second, I gotta erase this because it's bothering me. I'm not the neatest writer in the world, but even I have standards. All right. What we're going to do is, instead of just adding formic acid directly, we're going to add some HCl. Let's say I'll just try 1 molar and see how that works. I haven't practiced this one yet, so hopefully this doesn't give ridiculous numbers. All right, so we're going to start off with sodium formate, which means everything's going to be in this form at the beginning, and then we're going to add HCl, which means we're adding H+, so we're shifting the equilibrium over to the left side. All right, and we want to do it until we get to our target. All right. To do this, Actually, we've already done some of the calculations that would be necessary in the previous problem. If you remember, we did some calculations and we found that our ratio that we need of A minus to HA is 1.78. And that still applies here. All right? So we can also think of this as just being 1.78 to 1. All right, so here is a way I like to go about doing this. So look at your ratio, look at your fraction here, all right? 1.78 parts of this is A minus. 1 part of this is 2.78, right? So we have 1.78 mole of A minus, 1 mole of HA. So overall, you have 2.78 moles of stuff that contains formate or the protonated version of formic acid. All right, so that's what I'm going to start off assuming. All right, and if I assume that, that means that if this is the only thing that has that as a source initially, I need to start off with 2.7 moles of this guy. All right, so I'm going to say, just like we did last time, 68.01 grams per mole. All right. We know we want 2.78 moles of sodium formate, and we're trying to figure out how many grams that would be. So let me punch that out real quick. Comes out to be 189.1. I'm being lazy here, just writing formate instead of doing the formula. Sorry about that. All right, so that tells you half the problem there, right? We need to start off by weighing out this much sodium formate, dumping it in a container, all right? And overall, we have 2.78 moles of formate in the container. We need to convert 1 mole of this into formic acid. All right, so if we're looking at this, just to sort of remind us where we're at, now at the beginning we have 2.78 moles of the base form, and we have 0 of HA. We want to end up with 1 mole of this and 1.78 of this. Okay? And we're doing this by adding 1 molar HCl. All right, HCl is a strong base. It serves as a source of H plus, right? And as you add H plus, it's going to overload this side of the equilibrium, and the equilibrium will shift this way, right? So it would stand to reason that if we want to make 1 mole of HA, that we would need to have 1 mole of H plus. And since we know HCl gives off H plus in a 1-to-1 ratio, that means we need 1 mole of HCl. All right? So, one molar HCl equals 1 mole of the solute, and then the math's going to be pretty fuzzy here, but I think we're going to end up with a volume of 1 liter of solution. All right. One thing I see here that actually is this is going to violate our parameters of just making 1 liter of the solution, but I'll continue with it, and then I'll tell you how you could adjust this to fit within that parameter. All right. So basically what this says is you would need to take a container, dump, you would need to dump whatever that number was of sodium formate. I forgot what it was. Shoot. Let me Pre-punch it again because it's going to bother me otherwise. $68.01 times 2.78 equals 189.1. All right, so in summary, you can add 2.78 moles of sodium formate, which comes out to be 189.1 grams. You add a liter of 1 molar HCl, and basically that would be your buffer solution since you're trying to make 1 liter of it. Again, if you wanted to scale down on this, you certainly could, right? For example, instead of having a ratio of 1.78 moles to 1, you could have scaled that down by a factor of 10. You could have maybe said, I wanted 0.178 moles of A minus and 0.1 moles of HA, right? The ratio is still the same. It's just less material to work with. So either way, right? But this shows a second way that you can go about making these buffers. In a nutshell, you got to have both the acid and the base forms. You can either start with individual sources of both, or you can start with one and then use acid and base to convert some of it into the other material. All right. One last thing I want to go over, and that is actually talking about buffer systems that are in the body, right? So obviously we're water-based systems. So, we're going to want to keep fairly close to a pH of 7, although I think our internal pH is actually slightly alkaline. It's about 7.4. All right, but fairly close to neutral. All right, so we talked about, finding the right buffer if you're making one. Well, this applies to the body as well. So if you look at your buffer tables, right, and their pKa's, well, again, we sort of gravitate back to this guy, the second phosphate buffer system. All right, H2PO4 minus dissociating to H plus and HPO4 minus 2. We said that one had a pKa of 7.2. All right, so that's really close to the natural pH of the body and what we want it to be. And in fact, this is the buffer system that is commonly present in cells, human cells, or not just human, but other living systems as well, right? This helps keeps the cellular environment around the right pH that it needs to be. And, stuff is always importing and exporting in and out of the cell, so you're constantly changing concentrations. This helps keep things consistent, all right? As it turns out, though, there's actually another a very important buffering system in the body, all right? And that is the carbonic acid buffer system. Carbonic acid is H2CO3, all right, and it can decompose, why do I keep saying decompose? It doesn't decompose. It dissociates into H plus and HCO3 minus, which is known as the bicarbonate ion. Right, and it's got a pKa of about 6.37. So, looking at physiological pH, about 7.4 or so, we said previously that to be effective, a buffer needs to be within 2 pH units. So this definitely works. This is definitely within that 2 pH region. But phosphate is actually better in that regard, right? So a good logical question might be, okay, why is carbonic acid the buffer system in cells when, theoretically speaking, the phosphate buffer system should be better? Well, there's another complicating factor, and that has to do with breathing. Yeah, we breathe. We breathe air in. Why do we breathe air in? Well, we want oxygen from it, right? And we breathe out. What do we mostly breathe out? A little something called carbon dioxide. Yeah. We're constantly breathing in, breathing out gases, right? And one of the gases that we cycle in and out is carbon dioxide. And we cycle this largely through carrying through the bloodstream, right? We breathe in air, right? And at the same time, carbon dioxide waste from other parts of the body are transported through the bloodstream to the lungs where it can be expired out. Since carbon dioxide is both in free gas form and also dissolved in the bloodstream, that means there's a couple of different forms of it. There's the gaseous form and aqueous, dissolved in blood. All right? Funny little thing that carbon dioxide can do when it's aqueous and in the bloodstream, it can react with water. Carbon dioxide can actually pick up a couple of protons, and it forms H2CO3, carbonic acid, which we saw before, right? And then, just like we saw before, H2CO3 can decompose, or god dang it, dissociate. I have decompose on the brain today for some reason. Dissociate into H plus and bicarbonate. All right, so when you having this carbonic buffer system already present within your bloodstream, and since your bloodstream is consistently taking in and getting rid of carbon dioxide, this system provides a means for handling that. All right? Because